Now here's a trickier one. I want to know what's the maximum speed that a car can make a turn with a radius of 50 meters when the road is banked, okay? And we are going to ignore friction, meaning that you can do this even if there's no friction at all, even if you're driving on slippery ice. If you drive at exactly the right speed, you can still make that circle and you won't be sliding down, okay? So that sounds weird, but we're going to prove that right now. So let's look at two different perspectives. Okay, from the bird's eye view, there's my car. I cannot tell that this road is banked from this perspective. When I think about my forces, there's going to be no force in that tangential direction because I'm not going to change my speed. But I'm not sure what the force is in the radial direction. It's not obvious to me right now. So I'm not going to put something in here because I don't know what it is. Instead, let's look at the head-on view. So here's the car coming at you head on, and in this case, I'm on this incline. The car's going to be driving out of the page towards me. This angle here is 15 degrees. Let's draw my free body diagram. The z direction is still vertical, that's perpendicular to the plane of the circle, and my r direction is still completely horizontal. So these axes don't get tilted at all. If I draw the forces that are acting on me, I just drew this dotted line here. That's just kind of like just an imaginary line to show you where the ramp is. That's the ramp right there. When I show my forces, I'm going to have gravity pulling straight down, and I have the normal force. It's pointing up and it's perpendicular to the ramp, so it's pushing up like that. Okay. Now, in the previous weeks, whenever we had an object on an incline, we tilted our axes so that this direction became the vertical direction, and this direction became the positive x-axis. And then we broke our mg vector into an mg cosine theta in this direction and an mg sine theta in this direction. That's what we did in the past. We are not going to do that this time. We are not going to do that this time. The reason we're not going to do that is this object, we do not want it to slide down the incline or up the incline. It was useful to tilt the axes when the object was going to slide down in this direction or up in this direction. That made it very useful. This object is not going to accelerate down the incline. It's not going to accelerate up the incline. The direction that it will accelerate in is the r direction because it's going to be making a circle. So I want to keep the r direction because that's the direction of my acceleration. That's going to be the direction of my net force. So I want that to be a direction. I'm not going to tilt my axes. That means I'm going to take my normal force and break it into a component, one component pointing to the right and one component pointing up. And then I'll be able to look at the net force in the z direction and the net force in the r direction. So now we have to figure out how to break this up because it's not obvious to me that this angle right here is the same as 15 degrees. So if this angle is 15 degrees here, that's the angle of the ramp. That means that the angle between this blue line here and my horizontal is 15 degrees. Which means that the angle between my r-axis and this ramp is 15 degrees. Okay, so this is 15 degrees. So this angle here is not 15 degrees. It's going to be this angle that's 15 degrees. So that's my theta. That's the 15 degrees right there. So that means that if I want my vertical component would be adjacent to that angle. So I would get the cosine. And my horizontal component would be opposite of this angle, so we get the sine. So this is how it gets broken up. It's different than we're used to. Normally y and sine go together, but in this case the angle that they're giving me is with the vertical. It's with respect to the vertical, so that means the cosine goes with the vertical component and the horizontal goes with the sine component. Okay. Look through it again a few times just to make sure you believe that. But once we have this broken up, I can go back to my normal method, which is to look at my net force in the z direction and look at my net force in the r direction. Also, I could, if I wanted to, come back to this picture here and say, now I know what the force is in that r direction. It's n sine of 15. The full normal force from this perspective is kind of going to the right and coming out of the page. The part coming out of the page is the n cosine 15, but I'm not showing that in this perspective. But this doesn't really help me. I figured everything out really by looking at it from these two perspectives. Okay, so let's look at my net force in the z direction. My net force in the z direction is going to be, let's see, in the positive z direction I have n cosine of 15, and in the negative z direction I have mg. My net force in the z direction is always, always, always equal to my mass times my acceleration in the z direction. And in this case, the object is not going to accelerate in this vertical direction here. So a sub z is 0. So my net force in the z direction is 0. So I can say n is equal to mg divided by cosine of 15. I just took this expression equal to 0 and solved for n. Now if I look in the r direction, my net force in the r direction is simply n times sine of 15. And my net force in the r direction is always, always, always equal to my mass times my acceleration in the r direction. And my acceleration in the r direction is going to be equal to v squared over r. And here I'm looking at that maximum speed I can have without sliding around on there. So I know what my normal force is because I just solved for it here. It's mg divided by cosine of 15, so I can plug that in. So here, instead of n, I plugged in mg over cosine of 15. Then I had the sine of 15 left over. And then my m's cancel, so it does not matter what the mass is. And then I can just solve for my maximum speed. So this maximum speed is 11 meters per second. Now, what if we go faster than that? If we go faster than that, then this object would slide up the incline as it drives. What if we go slower than that? We would start to slide down the incline as we drive. And again, this means that if this is our speed, we can drive and drive on a road that's banked like this at this speed, and we will not rise or fall even if there's no friction. Even if there's no friction at all on here, if we drive at this speed, we'll just stay where we are on that ramp. We're not going to slide up or down the ramp. Here's an interesting example. So press pause, take some time to read through this, and then press play to see the answer. So what I would do to figure this out is I would think, this object is moving in a circle. Whenever an object moves in a circle, there has to be a force pushing it towards the center. There has to be a centripetal force, or else the object would not be able to move in a circle. So in this case, I could say, which force is the centripetal force? Which force is it that allows this penny to move towards the center of the circle? Which force is always pushing it inwards? Well, if there were no friction, then the record would spin by itself, and the penny would just stay in place. And it would be slipping all the time. The record would be slipping underneath it. That's if there were no friction. So in this case, it is static friction that is the centripetal force. That means that at every moment, what static friction is doing is pushing it towards the center. So when the penny is right down here, the static friction force is pointing it straight up. That's the only way to think about this problem. The static friction force is the centripetal force, and so that's the force that's pushing it towards the center. So static friction is pushing it up and towards the center.